Welcome to our Chapter 5 problem solving video. And so we're going to go over a couple problems from the Chapter 5 homework. Again, we aren't really concerned with sig figs anymore. We're done with Unit 1. You can forget about sig figs until the final. There'll be one or two questions on the finals that relate to sig figs, and that's it. So now we're just doing simple algebra, round your answers to simple numbers. So in this case, we have two samples of two different elements that we're trying to figure out if they're the same compound. So if we have different arrangements of the same atoms, we can have different chemicals or different compounds. And so the law of constant composition was our law that basically said any given chemical, water is one example, will always have the same combination of the same elements. It'll always have two hydrogen atoms with one oxygen atom. In this case, we want to see if these two samples of potassium and bromine are the same compound. Are they potassium bromide, or are they some other version of potassium and bromine mixed together? The way we do this is we take the mass of each given compound. It doesn't matter which mass we take, as long as we keep it consistent. We can take the mass of potassium first, or we can take the mass of bromine first. We're going to put one in the numerator, one in the denominator. We're going to figure out what the ratio of these two elements are to each other. If those ratios are the same, it's almost guaranteed that they're going to be the same chemical. There are some exceptions when we get into chemical and empirical formulas. Sometimes, the empirical formula and the chemical formula are different, but that's not what we're doing right here. We're just seeing if they match. So in this case, we have pretty good agreement. We take the ratio of potassium to bromine. We could have taken the ratio of bromine to potassium. Either one's fine. We got a pretty good agreement. So this is about, a 2% disagreement, 1% disagreement, somewhere in there. That's not enough to think that these are different chemicals purely from this test. So we would assume and explain that these are the same. The difference between the two numbers or the two ratios could be explained by the error of a balance or something as simple as that. So these would be essentially exactly the same, and we would assume that these are the same or the same chemicals, not just the same elements. All right, so moving on to the next one, we want to classify these as ionic or molecular. Remember, ionic compounds are compounds that have a big difference in electronegativity, where molecular or covalent compounds have less of a difference between electronegativity. Ionic, there's full isolated charge. One partner will become an anion and steal all of the electrons. One will become a cation and give up its electrons. Whereas in a covalent compound, we have a sharing of electrons. Not always a perfect sharing of electrons, but a sharing of electrons rather than a full taking and giving of electrons. So in general, we have covalent compounds if our elements are from the right side of the periodic table or to the right of the transition metal series. If we have chemicals that are both on the right side of the transition metal series, which we'll call nonmetals, and something that is a metal, the transition metal series, and to the left, the alkali metals, the alkali earth metals, those would be ionic. So sulfur and oxygen are both in the P block, so that's going to be a covalent compound or a molecular compound. Again, hydrogen's kind of special. We consider hydrogen to be a part of, the main, or not the, sorry, it is a part of the main group, but we consider it to be a non-metal in most cases. Some people in physics will try to make metallic hydrogen, but that's a very special case. Hydrogen's typically a non-metal. So in this case, we have a bunch of non-metals. We're going to have a molecular or covalent compound. Same with carbon dioxide. Palladium oxide, PDO. This is not lead oxide, but even if it was lead oxide, we have a metal and a non-metal. This is going to be an ionic compound. So moving on, now we want to take elements from the periodic table and make compounds from them. Now, some of these will be molecular, most of these will be ionic, but we can still see how much or how they're going to pair up based on their charge prescribed by the periodic table. So remember, lithium is an alkali metal. It's in group 1. So it always has a +1 charge. So nitrogen is always is always -3 or +5. If lithium's always positive, nitrogen's definitely going to be negative in this case. So it's going to be -3. We're going to need 3 lithiums to cancel out the charge of this one nitrogen. Oxygen's -2, fluorine's -1. This is all based on where their relative position is in the periodic table. As we get further or closer to the noble gas configuration, the magnitude of the charge will increase. If we're giving up electrons, we're giving up the negative charge thing, we'll become more positively charged, or positive, a cation. If we gain electrons, we're going to become more negative or become an anion. So barium is an alkaline earth metal. It's always going to take a +2 charge. So we'll have to balance these out with these respective charges. Aluminum is a little bit different though. Aluminum can be plus or minus, depending on what it's paired with. So aluminum bonded to hydrogen, aluminum forms a negative charge. But aluminum bonded to something that's more electronegative than it, it'll form a positive charge. Nitrogen, oxygen, fluorine are all more electronegative than aluminum, so they're going to steal the electrons rather than give up the electrons. Aluminum's going to give up its electrons, so it's going to take a +3 charge, not a -3 charge. So we can do all of these various compounds. Lithium being +1, nitrogen being -3. We need 3 lithiums to balance it out. 2 lithiums for the -2 charge on oxygen. 1 lithium for the -1 charge on fluorine. Barium, we already said, is a +2 charge. So in this case, we have a little bit of a more complicated arrangement. We have 3 bariums and 2 nitrogens. Remember, we can put their charge up in the corners and do kind of the X or cross rule, where barium has a +2 charge, so that 2 goes down by the nitrogen. Nitrogen has a -3 charge, so that 3 goes to the barium, and that guarantees that they're going to be balanced. Then you just have to make sure that you have the lowest whole number ratio. You can't divide 3 or 2 by anything other than 1 and still get a whole number, so we're good. If this was 6 and 4, we'd want to divide those both by 2 to get the lowest whole number ratio between the two. Barium and oxygen have the same magnitude of charge, so it'll just be a 1-to-1 chemical compound. 1 barium +2 charge for every 2 fluorines that have a -1 charge. Aluminum, like we said, is less electronegative in all these cases, so it's going to be a +3. Aluminum to nitrogen, aluminum nitride, will be a 1-to-1 or a binary compound. We have aluminum oxide. Again, we could do the cross rule where aluminum has a +3, that 3 goes down to the oxygen. Oxygen has a -2, that 2 goes down to the aluminum. They're perfectly balanced and neutral. +3 for the aluminum, we need 3 fluorines that are always -1 to cancel them out. Alright, so again, I'm not going to focus too much on naming in this class, but this is the chapter on naming, so we're going to have some of these problems in the homework. You'll have maybe one naming problem on the exam, in the final, but in general, I just want you to be able to understand what we're talking about. So if I say something, you should be able to relate something else to it that has meaning to you. So remember, we have for nonmetals, so these are all nonmetals. We don't have any metal compounds in here. We have a little bit different naming rules for metals, depending if they're S block metals or D and F block metals. D and F block metals that have variable charge, we designate what the oxidation state is, iron 2 or iron 3 chloride. Whereas sodium is always +1, so it follows more of the rules that the nonmetals would. So however many there are, you get a specific prefix. The first chemical, or the less electronegative chemical, doesn't get a prefix if there's only one of them. So if there's 1 carbon, we don't say monocarbon or you don't say monocarbon. However, if we have 1 oxygen at the end, we do say monoxide. So 1 carbon, 1 oxygen. Remember, our naming rules are mono is 1, di is 2, tri, tetra, penta, hexa, hepta, octa, nona, deca, so forth and so on. So carbon monoxide is just going to be CO, disulfur tetrafluoride, 2 sulfurs, 4 fluorides, or fluorines. Remember, the second nonmetal gets the IDE suffix. We cut off the last 2 vowels and add IDE. Dichlorine, it's the first one, the less electronegative one, so it keeps its name. Monoxide. Phosphorus, the first one doesn't get the mono designation, it just gets its base designation if there's just one of them. Penta is 5, fluoride. Boron tribromine, or bromide, is more correct, is appropriate. And diphosphorus pentasulfide is going to be P2S5. So, again, I don't really care too much about naming in this class. You are going to need to memorize every single one of these acids if you go into further chemistry classes. In this class, I don't care. I'm not going to test you on naming acids. What I do want you to realize is that phosphoric acid, hydrobromic acid, and sulfurous acid, 2 of these sound just like our polyatomic ions or our elements, whereas one of these has a hydro in front of it. Anytime you have a hydro and then an elemental acid after it, that's going to be a binary acid between hydrogen and that specific acid. Whereas if you don't have that hydro prefix, you're going to have an acid with hydrogen and some type of polyatomic ion. So in the case of phosphoric acid, the polyatomic ion is phosphate. Phosphate is a -3 charge, so we need 3 hydrogens. This is a polyprotic or a triprotic acid. Hydrobromic acid, hydrobromic, it's hydrogen and bromide. There's nothing else. There's only 1 hydrogen, 1 bromide. If there were multiple bromides, this would be a different acid. That would be based off the functional group that we name for 2 bromides together. Sulfurous acid. So this is our sulfite polyatomic ion. It has a -2 charge, so it'll have 2 protons that counter it out. If you have any questions about this stuff, make sure to reach out or visit me in office hours. Otherwise, I'll see you in our next lecture in lab.